micrófono. Voy a apagar mi micrófono.
Ok. Buenas tardes. En nombre del Centro de Ciencias de la Atmósfera, agradecemos su participación en la tercera sesión del Panorama Actual de las Ciencias Atmosféricas en su edición del 2020. A través de la videoconferencia se registran más de 500 participantes, a los que se les agradece mucho su interés. Además, otras personas nos están siguiendo a través de las redes sociales. Estas sesiones son grabadas y también se podrán seguir a posteriori a través del Facebook. En cuanto a las preguntas, las personas asistentes pueden hacer preguntas en el chat dirigidas al anfitrión. Las preguntas son gestionadas sobre la marcha en función de los tiempos y se responderán hasta el final. Por una cuestión de tiempos, se leerán únicamente las preguntas, es decir, los saludos y felicitaciones se le pasarán al conferencista, pero posteriormente al evento. Y a continuación, el doctor Alejandro Jaramillo, quien es investigador del Centro de Ciencias de la Atmósfera, nos presentará la semblanza del conferencista invitado, que es el doctor Roland Madden, del National Center for Atmospheric Research de Estados Unidos. Adelante, Alejandro.
Bueno, muchas gracias, Carles. Buenas tardes a todos. Sean bienvenidos a nuestro seminario de Panorama Actual de Ciencias Atmosféricas que organiza el Centro de Ciencias de la Atmósfera. El día de hoy tenemos el gran honor de contar con la charla a cargo del doctor Roland Madden. Creo que todos los que estamos en ciencias atmosféricas, en particular en meteorología tropical, hemos escuchado sobre el doctor Madden, al ser codescubridor en 1971, junto con Paul Julian, de la oscilación que lleva su nombre, la oscilación de Madden-Julian. La oscilación de Madden-Julian es un fenómeno que domina la variabilidad intraestacionaria en los trópicos y que tiene múltiples influencias tanto para las zonas tropicales como sus teleconexiones con los extratrópicos. Esta oscilación es, sin lugar a dudas, uno de los fenómenos más estudiados en la meteorología tropical y también uno de los grandes misterios aún por resolver, y que se encuentra en el punto intermedio entre el tiempo meteorológico y el clima. El Dr. Madden aprendió meteorología básica en la Universidad de Texas A&M como oficial de la Fuerza Aérea de los Estados Unidos de América y ejerció como pronosticador en Cabo Cañaveral, en la Florida, durante su estancia en la Fuerza Aérea. Luego de 4 años en la milicia, comenzó sus estudios de maestría en la Universidad de Chicago, trabajando para Ted Fujita. Al finalizar su maestría, se unió al Centro Nacional para la Investigación Atmosférica en Boulder, Colorado, más conocido por sus siglas NCAR. En 1978 obtuvo su doctorado en la Universidad de Colorado State, bajo la dirección de Westward-Haurwitz, en donde sus intereses se concentraron en las observaciones meteorológicas tropicales y de gran escala, el clima y los límites de la predicción a largo plazo. Actualmente es investigador emérito de NCAR, en donde continúa sus intereses en la gran escala y en los modos normales de las ondas de Rossby-Haurwitz, de las que nos hablará hoy. Ese tema es muy apasionante y fundamental para los desarrollos teóricos que permiten comprender la dinámica sinóptica. Se podría decir que comenzó con los trabajos de Laplace en el siglo XVIII sobre la teoría de las mareas y con las contribuciones revolucionarias de Rossby y Haurwitz en la década de los 40. Demos pues la bienvenida al Dr. Madden. Pueden hacer sus preguntas en la herramienta de preguntas con el símbolo de interrogación en la aplicación. Todas las preguntas son bienvenidas. Las pueden hacer en inglés o en español y yo trataré de traducirlas. Y vamos a cambiar ahora al inglés. Thank you, Roll, for accepting this invitation. It's a real honor for us to have you here. The seminar is now yours. I'm going to give you the permissions. I'm going to make you presenter right now. Thank you very much for being here today.
Is it okay? Can you see my screen?
Yes, it's
Okay.
looks very good.
Okay. Buenas tardes y gracias. It's an honor for me to be part of your seminar series. I would have liked to have been enjoying your campus and seeing your faces, but under the circumstances, that's not going to work. In that vein, I thought maybe you would like to see the office from which I'm speaking from. This is the National Center for Atmospheric Research in Boulder, Colorado, USA. It sits on a mesa of southwest of the city of Boulder. Boulder's a city of about 110,000 people. And from the vantage point of the building, if you look north or east, you see the city, and to the west, you see the foothills here of the Rocky Mountains. And among architects, it's a famous building. In fact, I've got this picture from greatbuildings.com. And I think none of you will be surprised that another building on that list is the library building on your campus. Unfortunately for me, this was my office before COVID. Now my office after COVID is a little more humble, and this is my house in South Boulder, and I am sitting in this house giving this lecture. It's my first actually remote lecture that I've given. And anyway, I think I have that in common with many of you. You're probably in your homes or in your apartments. Okay, I think we're ready maybe to start. And I would like to say gracias por escucharme en inglés. So I'm going to talk about normal mode Rossby-Haurwitz waves. My talk has two parts. Part one, I'm going to outline the results from theory leading to the predicted structures and periods of normal mode Rossby-Haurwitz waves. And in part two, I'll present evidence of these predicted structures and periods in 3 years of 2010, 2011, and 2012 ERA interim analysis. I'll spend about 20 minutes on each of these parts. So the theory goes back over 200 years to the Frenchman Laplace, who formulated which are now called the Laplace tidal equations. So fluid motion on a sphere. And this was about 1800. Huff, an Englishman, showed about 1900, 100 years later, he showed that the horizontal structures of the waves predicted by the Laplace tidal equations can be expressed as sums of associated Legendre polynomials. They're not called Huff functions. I'll touch on this early work later on in the talk, but I want to start with the simplest approach to these Rossby-Haurwitz normal modes. And that was presented in Rossby's famous 1939 paper. Non-divergent waves, he talked about non-divergent waves on a plane. And this simple approach, this plane is the assumption of a plane instead of a sphere, and also assuming non-divergence, illustrates the basic dynamics. Rossby came to the United States in 1926 from Sweden. He was 26 years old. And during the 1930s, he was a professor at the Massachusetts Institute of Technology. That's when he did the work on the 1939 paper. Okay, so this is the reference to the paper down here. And again, it's non-divergent Rossby waves on a plane. And the principle is the conservation of the absolute vorticity. And the vorticity is a measure of the rotation, and it's made up of two terms, F, which is the planetary vorticity, and it's equal to 2 omega sine phi, where omega is the rotation rate of the Earth, and phi is the sine, or phi is the latitude. So omega goes from, F, the planetary vorticity, goes from 2 omega at the pole to 0 at the equator. So by virtue of the rotation of the Earth, a parcel on the Earth automatically has this planetary vorticity. Then in addition, there might be some relative vorticity. And relative vorticity comes about because of shear in the flow or curvature in the flow. Well, based on this principle of conservation of absolute vorticity, Rossby was able to come up with a very simple wave equation that expresses the phase speed of a wave, say on a meteorological chart. And it's equal to the background wind, which is advecting the wave. And this second term captures important aspects of the normal mode Rossby-Haurwitz waves. First of all, the minus means that the waves are going to be moving toward the west. And the fact that the wave speed is proportional to L squared, that's the wavelength. It means that the largest scale, the waves with the longest length, will move fastest toward the west without, if there were no effect of background winds. Beta is the rate of change of this planetary vorticity with respect to y, the north-south coordinate. I have this figure to kind of illustrate some of the dynamics of these normal mode Rossby-Haurwitz waves. Again, the important thing is that the absolute vorticity is a constant. And let's assume that this is along a latitude line, this line here, and it goes from west to east, and that there's a wave in the data which is indicated by the north-south wind here, with arrows going up, meaning a south wind, a wind blowing from the south to north, arrows going down, a wind blowing from the north to the south. So everywhere where the winds are coming from the north, the planetary vorticity of a parcel is decreasing because it's going from the pole, where F is a maximum, to the equator, where F is 0. So that means, that means that in this region, the relative vorticity has to increase. And the opposite is true over here. The relative vorticity has to decrease because the planetary vorticity of the parcels is increasing. Now, the relative vorticity of a wave like this is given by dV. V is this north-south wind, dx. So every place that V is decreasing, the relative vorticity is negative. dV dx is negative. Everywhere it's increasing, dV dx is positive, and then negative again here where V is decreasing. So you can see that the maximum relative vorticity located here is going to move to the west where the relative vorticity is increasing. And similarly, the minimum in the relative vorticity will move toward place where the relative vorticity is decreasing. So this simple approach of Rossby's famous 1939 paper gave a simple wave equation, and also the principle of the conservation of absolute vorticity reveals some of the important aspects of the dynamics of the Rossby-Haurwitz waves. But the approximation of using a plane is not a good approximation for very large scale waves, because very large scale waves are going to feel the sphericity of the Earth. So Rossby used the non-divergent waves on a beta plane. It's called a beta plane because df dy, the rate of change of this planetary vorticity with y, is called beta. So in 1940, Haurwitz got a little more realistic because he used non-divergent. He looked at non-divergent waves on a sphere. So he eliminated this plane, the approximation of the plane. Bernhard Haurwitz came from Germany, and he came to MIT, Massachusetts Institute of Technology. He was invited by Rossby in 1932. By the end of the 1930s, he was at the University of Toronto. He was able to show that the structures of the waves, non-divergent waves on a sphere, were associated Legendre polynomials. And these happen to be the structures of 20 different wave modes, and they're the structures of the stream function. And you'll be seeing a chart similar to this again, so I want to explain it. Each row represents a zonal wave number. So every wave mode in this row has a zonal wave number of 1. So that's one wave around a latitude. And this row is zonal wave number 2, then zonal wave number 3, and zonal wave number 4. Each column has a different latitudinal structure. And these little panels, they show the latitude in radians. So for example, this would be the South Pole, and this would be the North Pole. This N is sometimes called the Meridianal Index, and it tells the number of zero crossings of this associated Legendre polynomial between the North Pole and the South Pole. So this column here is for n equals 0, and there are no zero crossings. So this particular wave mode will be zonal wave number 1 in the east-west direction, and in the north-south direction, it's in phase at all latitudes. So if you look at any longitude and your stream function were, say, positive in the northern hemisphere, it's going to be positive in the southern hemisphere. It will be in phase across all latitudes. And that's as opposed to the n equal 1, which has 1 zero crossing between the poles. And this wave mode it would have in the stream function, if it were positive, again, it'd be wave number 1 in east-west direction. But if it were positive in the northern hemisphere, it would be negative, out of phase across the equator. Okay, so now we have first the simplest approach, which was the non-divergent waves on a beta plane. Haurwitz introduced a little more realistic approach by using spherical coordinates. So he looked at non-divergent waves on a sphere, and he showed that the horizontal structures that we might look for in data would be associated Legendre polynomials. Now we go back to the work of Laplace around 1800 and Huff around 1900, because the Laplace tidal equations describe divergent waves on a sphere. So they're even a little more realistic than Haurwitz's approach. Their horizontal structures, it turns out, Huff showed that their horizontal structures are sums of associated Legendre polynomials. And these sums of associated Legendre polynomials are now called Huff functions. This is a chart again where the first row is zonal wave number 1, wave number 2, wave number 3, and wave number 4. And each column is a different meridional structure. The dots, again, this is would be the South Pole, this would be the North Pole for this particular mode. This would be the S equal 1, N equals 0 mode. And the dots are the single associated Legendre polynomial, which are the solutions or the structures for the stream function for the non-divergent case on a sphere. That's Haurwitz's paper, 1940 paper. This is at least theoretically, the more realistic latitudinal structure. This is the Huff function. and its sums of these associated Legendre polynomials. You can see that the single associated Legendre polynomial for the non-divergent case is a pretty good approximation to the Huff functions for the atmosphere. And the reason being is that the leading term in the sum of, here I have an example down here. Let's say this is the Huff function for zonal wave number 1 and Meridianal Index 2. So it'll be this mode. And these are the single associated Legendre polynomials. So this Huff function is a sum of these associated Legendre polynomials. But the factor out in front of the associated Legendre polynomials is biggest for the leading term. It's like 0.99. The second term is 0.11. So this Huff function, the solid line, is this associated Legendre polynomial, a single one, multiplied by 0.993, plus the 1,4 associated Legendre polynomial, that's this dotted, but it's multiplied by a smaller number. So that it turns out that these leading terms, which are the single associated Legendre polynomial, dominate the sum. And that's why a single Legendre polynomial is a fairly good approximation for the Huff function. So now we've seen the simplest case, non-divergent waves on a beta plane, then the non-divergent waves on a sphere by Haurwitz, Laplace tidal equations, which describe divergent waves on a sphere, which in this case, the horizontal structures are sums of associated Legendre polynomials, which are called Huff functions. Now I'm going to show some results from Akira Kasahara's modeling work to get an idea of the theoretical prediction for vertical structure and for wave periods. This is a picture of Akira Kasahara in the National Center for Atmospheric Research computer room in about 1969. You can see in the background here, in 1969, telephones looked different, computers looked different. Data storage was on tapes, which were probably order 25 or 30 centimeters across, and they had to be mounted on these tape drives. Besides all those things being different, it turns out fashions were different in those times too. If you look at the pants on this computer operator, you don't see pants like that too much anymore. So Kira showed that the vertical structure is that of an external wave. Many other authors have shown this as well. And what I mean, when we mean by an external wave, is that the wave is the Rossby-Haurwitz normal modes are in phase in the vertical. There's no slope. The energy of the wave decreases in the vertical, but the amplitude increases slightly because the density falls off so rapidly that even though the energy is decreasing, the amplitude increases slightly. So now we have an estimate that the vertical structure of the waves, when we look for them, should be like this in phase in the vertical external waves. The wave periods were estimated by including December, January, February winds in a global shallow water model. And that's a paper by Kasahara in 1980. And here's the results from that work. And I've included a sort of a reminder up here. We're dealing with these 20 modes, zonal wave number 1, 2, 3, 4, and the various latitudinal modes. And so the layout is just the same here. And these are periods in days for the various modes. So this largest scale mode, which is zonal wave number 1 in the east-west direction and has no zero crossings in the north-south direction, is predicted to move all the way around the world in 1.2 days. And the second mode is predicted to move around the world. It would have 1 zero crossing in the stream function. It would move around the world in 4.85 days. This particular mode has been observed for many years, and it's usually referred to as the 5-day wave. This mode is referred to often as the 10-day wave, and this one as the 16-day wave. But you can see that Kasahara's theoretical prediction suggests it's a period should be closer to about 18 days. So now theory predicts a wave structure, which are Huff functions or sums of associated Legendre polynomials. And also the vertical structure theory predicts. It's in phase in the vertical, and it has small amplitude growth with height. And Kasahara predicts wave periods with December, January, February winds, which we just looked at, these wave periods. Oh, and incidentally, he couldn't find a period for these waves because these waves are moving so slowly that the background wind can diffuse them and change their period, and in fact, sort of eliminate them. They can't be identified, or they couldn't be identified in his modeling work. Okay, so now we have this from the theory. We can move on to part 2 and look for some evidence of normal mode Rossby-Haurwitz waves. Previous observations go back to at least 1954. DeLand in 1964 talked about the 5-day wave. Maybe the most famous papers are Eliason and Machenauer and Tellus in 1965 and in 1969. And in the interim, there's been many, many more. In fact, there's been several reviews about observations of these normal mode Rossby-Haurwitz waves. The evidence I'm going to show is from 3 years of 4 times daily vorticity fields from the European Center for Medium Range Weather Forecasting, their interim analysis, 2010, 2011, and 2012. So I have 4 maps per day at several levels in the vertical. And the vorticity fields, their horizontal structure look like the stream functions, which we've been looking at a little bit in previous slides. So the predicted vertical structure, I approximated by just vertically averaging these vorticity fields from 850 to 100 hectopascal. So now I have one map every 6 hours of the vertically averaged vorticity. And that approximates the theoretically predicted external nature of the theoretically predicted waves. Then I took these fields of vertically averaged vorticity and projected them onto the associated Legendre polynomials. So I didn't use Huff functions. I used, as a first approximation, single associated Legendre polynomials. So each vertically averaged field was projected onto these various, well, here there's the 20 modes. And so one gets an amplitude and a phase for each one of the projections. And we're hoping that these projections have physical meaning, and in fact that what they represent are the normal mode Rossby-Haurwitz waves. So I go back. When I do that, I have these waves. I can now look at any one of these modes and see where the latitude and longitude of the projection is, latitude and longitude of the northernmost maximum. And here's an example. Here's our little reference. This is an example of this, what's called the 16-day wave often. It's the S equal 1, N equal 3 mode. So it's the S equal 1, N equals 0, 1, 2, 3 mode. It's this mode. This is what it looks like in vorticity or stream function in latitude. And what I've plotted here is the spatial sine coefficient versus the spatial cosine coefficient. You can think of this sort of as a map where this is the North Pole. This is the Greenwich Meridian along here. This is 90 West. This is the date line, and this is 90 east. Each value then is where the ridge of the northernmost value of the northernmost high pressure area of this particular mode is, in this case, on the 16th of January, 2010 at 00Z. So there's one plotted per day. So this is the 17th at 00Z. So there's 1, 2, 3, 4, and around. Turns out it's 19 days for this wave to move. First, it's near 90 west, and then it moves westward to the date line, and then further westward to come to 90 east, and then back around to the Greenwich meridian. So it's about 19 days. Kasahara predicts 18.39 days. This is one example that I found, but now the question is, we have all these modes. How typical is this for the 3 years, and how typical is it for other modes? And one way to get at that is spectrum analysis. The spectrum analysis gives us variance and covariance or correlation as a function of frequency. So with this kind of rotation, we would expect that the spatial sine coefficient and spatial cosine coefficient would be coherent at the predicted frequency, in this case around 18 days. Should be coherent at 18 days if this is happening a lot in the 3 years. And the real component, or the spatial cosine coefficient, should lead the imaginary coefficient by a quarter of a cycle. You can see here when the imaginary, the sine coefficient is about 0, the cosine coefficient is a maximum. And then a few days later, should be about a quarter of a cycle later, the imaginary or spatial sine coefficient will be a maximum, and the cosine coefficient will be 0. So there's two variables. In this case, there's 2 variables we might look at: coherence square and phase. Hayashi in 1971 presented similar information, only he did it in a single variable. He called it the Westward Variance, and it's equal to this value here, which is 1/4. This is the power spectrum of the spatial sine coefficient at a frequency f. So it tells us what the variance of the spatial sine coefficient is at a frequency f. And for the 1-3 mode, it would be, the f would be 1/18 days that we'd be looking for. That's what the theory suggests. This is the the spectrum for the cosine coefficient at frequency f, and plus twice the quadrature spectrum. That is, the quadrature spectrum is a measure of the covariability between these 2 time series, but one time series is shifted with respect to the other by a quarter of a cycle. So it tells us the sort of out of phase. It's actually one of the powerful aspects of spectrum analysis. You can see correlation that is not in phase, but correlation that is out of phase. So we're now going to compute the spectra of these various quantities, and I'll show you the westward variance and also the coherence squares. So we have approximated the vertical structure that's predicted by vertically averaging the vorticity from 850 to 100 hectopascal. We've approximated the theoretically predicted structure by projecting vertically averaged vorticity onto the associated Legendre polynomials. Now we're going to look and see if these projections are consistent with by showing coherence and phase and Hayashi's westward variance as a function of period. Are there going to be relative maxima in the westward variance at the theoretically predicted periods for the various modes? Here's an example again of the 16-day wave. So that's the S = 1, N = 3 mode. remember when we plotted it for that one case, it showed this kind of this westward propagation took about 19 days. Okay, this now is the spectrum, and the solid line is Hayashi's westward variance, the heavy line. The coordinate axis here is the frequency in cycles per day, runs from 0 to 0.25 cycles per day. So it's like infinite period to 4-day period. The vertical line is Kasahara's prediction with realistic winds, 18.4-day periods. And you can see the westward variance has a marked peak, but it's maybe at 20 days. It's at a longer period than theoretically predicted. And I haven't shown the phase, but I do show the coherence squares, which are indicated here. And the phase through this whole way does show that this real coefficient leads the imaginary coefficient by 1/4 of a cycle, which is consistent with westward propagation. And also the coherence square gives the opportunity to do a little statistical test, because the 95% confidence level for a null hypothesis of 0 coherence between these this real and imaginary spatial coefficients is about 0.1. And 0.1 lies down about here. And what this means is that if in fact these coefficients, spatial coefficients, are not coherent at all, that's my arrow, they are not coherent at all, only 5% of the estimates would exceed 0.1 sort of randomly. So this coherence is very statistically significant. Okay, now this is a busy slide, but it's sort of the summary of all the observations. And again, here's our reference. These are latitudinal structures of our various wave modes. Here's zonal wave number 1. And I've added for zonal wave number 5 in this figure. So this reference only pertains to these. I haven't shown you what the structures would be for zonal wave number 5. The heavy line is the westward variance of Hayashi, and the thin line is the coherence squared. For zonal wave number 1, you can see here, and the dashed red line is Kasahara's prediction, theoretical prediction of the period. And you can see that for this mode, it's moving very fast. It would have about a 1.2 day period. There's a very sharp peak in the westward variance right at the predicted period. And this mode is the 5-day mode. It also has a relatively sharp peak. The 10-day mode has maximum westward variance, but it's not so sharp. And this is the one we just looked at in a little more detail. Now, I suppose it's not surprising that these very fast modes have the sharpest peaks, because the zonal winds can't blur them out, because the modes are moving so fast with respect to the wind. And as you get to slower moving and smaller scale, spatial scale modes, they get smeared out. And in fact, down in the lower right-hand corner, here, the modes can't even be detected, because the winds have smoothed them out, and they're not evident at all. To first approximation, well, we can make an estimate of zonal scale by the sum of S, the zonal wave number, plus N, this Meridianal Index. And the first approximation, S plus N equal to 5, it lies along this diagonal. And every one of the modes where S plus 1 equals to 5, one could argue there is evidence for the existence of the mode in this 3 years of data. Many of the, again, it's the largest scales, which are up here, are pretty marked, and these are the fastest moving. The less fast moving and smaller modes are not marked so well. For example, S equals 5, N equals 0. There's a little bit of peak in westward variance. The coherence square is significantly different from 0 though. So anyway, what I'm saying is the first approximation, all these wave modes up to the left of this diagonal, I think there's evidence for the waves. So this is of academic interest. I think this correspondence between observations and theory is amazing. With meteorological data, you don't often see this kind of thing. So, but does it have any other value? I mean, is it important in any other way? Okay, here's our reference again. And this chart here is based on an earlier empirical orthogonal function analysis in which we could approximate the variance explained by each of the modes. So here's zonal wave number 1, and these are the meridional indices. If we add this variance up, we get 11, 17, about 18% of the variance of zonal wave number 1 can be explained by these large scale modes. And for zonal wave number 2 and 3, the explanation, or the sum of this, is about 12. These waves, I guess in this analysis, we couldn't identify these modes with the EOF analysis. And the question marks, it wasn't clear exactly what the variance was. So this is a sizable amount of variance. Okay, so in summary, since 1954, there have been numerous studies using different data, different analysis techniques, and they've shown evidence for normal mode Rossby-Haurwitz waves. The overall correspondence between observations and theory is, in my opinion, among the best of any in meteorology. Rough estimates of the variance explained by the normal mode Rossby-Haurwitz waves range from about 12% for zonal wave numbers 2 and 3 to about 18% for zonal wave number 1. Now, what are some further questions? Okay, what are the details of the wave forcing? These normal modes are free waves, but they need something to excite them. And if we understood more how they're excited, we could anticipate times when they'd be more active. Another question is, how well do forecast models handle free Rossby-Haurwitz waves? This problem of free Rossby or normal mode Rossby-Haurwitz waves in forecast models has been known since the beginning of numerical weather forecasts, and it's been treated in the literature. But to the best of my knowledge, I'm not familiar with any studies that have quantitatively linked the normal mode Rossby-Haurwitz waves with the skill or value of a forecast. And I'm going to close by referencing a paper that's 70 years old that elaborates on this idea of how models handle free Rossby waves. And it's a paper written by Jules Charney and Arndt Eliasson in 1949. They were commenting on one of the first numerical weather forecasts, and they say that the agreement of an actual 24-hour forecast, and they did it with a simple barotropic model that vected vorticity. They say that the agreement with observations was better than had been expected, but there was also a marked discrepancy, a deep and extensive trough in the Western Pacific and a wedge in the Eastern Pacific were predicted to move rapidly westward, but they were observed not to move at all. They go on to say, the persistence of the Pacific trough and wedge system suggests the explanation that the motion is composed of a traveling free perturbation and a permanently forced perturbation produced by the action of geographically fixed perturbing forces. So this free would be our normal mode Rossby-Haurwitz waves. The forced would be the time mean waves that are forced by, say, mountains and heat sources. And so this problem was understood 70 years ago. And with that, I will say muchas gracias and open it up for questioning.
Thank you, Raul. It was very interesting, your presentation. It was very beautiful the way you presented the historical part and how you get to that point into the research. I'm going to read first a question by Christine Dominguez. So she says, hi, thank you for your presentation. It was pretty great. I would like to ask if the Rossby-Haurwitz waves can be important for short range forecasts or perhaps for the medium range forecast. If so, how could they impact?
Okay, so the question is, could these normal mode Rossby-Haurwitz waves be important for short or medium range forecasts? And I didn't understand the end. If so,
yeah, that's the question. How this equation impact to the forecast? How these waves impact the forecast?
Since they, especially wave 1, explains as much as 18% of the variance of wave 1. If the model, the forecast model, does not have the climatology correct, it doesn't have the, say, the forced mean waves correct, then when it's initialized with observations, it can distribute the energy between the forced waves that aren't going to move and these free waves that will travel rapidly westward. It can distribute that energy not correctly. And so I think that, in fact, they can have effects on short and medium range forecasts.
Okay, thank you.
Is that answering?
Yeah. Yes. The next question is by Dr. Graciela. She asked, do these waves have a seasonal cycle? Seasonal cycle.
I should know the answer to that. I think they're more active in the winter, but I am not positive about that. I'm sure they have a season. I suspect they have a seasonal cycle, and I would guess they're more active in the winter. But that's something that probably could be looked at more closely.
Okay, the next question is by Werner Ochoa. And he asks, is there evidence of any interaction of the NJO with Rossby waves?
Okay, in fact, the reason I started to look at this, I started to look at vorticity fields, is because ultimately I was interested in seeing how these waves might be excited. And I thought with vorticity, I could look at heating and maybe stretching of vortex tubes or whatever forces of vorticity. And I had in mind actually one of the forces being the MJO, because of all the added convection near the equator. If maybe when they're very active, they might excite these normal mode Rossby-Haurwitz waves. I haven't gotten anywhere on that so far, but I guess the answer to his question is, I think it's possible.
Okay. The next question is by Julio Marin. He asked, which atmospheric phenomena are most influenced by these Rossby-Haurwitz waves?
Which atmospheric, I guess I don't understand.
Phenomena. Which phenomena are more influenced by these modes?
Let's see. Well, these modes, of course, affect the geopotential heights, the U winds, the V winds. In fact, I have, well, I don't know if this is really an answer to the person's question, but I have, I don't know, can you see this figure?
Yes.
It says Huff Functions on the top.
Yeah.
Okay, I've been showing you the latitudinal structure of the vorticity, but there's also, I mean, the U wind, for the east-west wind, for example, looks like this dashed line, and the north-south wind looks like this dotted line, and the geopotential height or surface pressure looks like this solid line. So I don't think this is really an answer to the person's question, but I guess the point I'm making is that all these variables are wrapped up in these normal mode functions.
Okay,
I don't know if I can do any better for that one.
The next question is by Dr. Arturo Quintanar. He has two questions. The first one says, it appears that the Rossby-Haurwitz normal modes exists in isolation. Is that because there are free modes of a barotropic atmosphere only?
Yes, I mean, even random forcing, they will be preferentially forced.
Okay. His second question is, can we envision wet Rossby-Haurwitz normal modes in the tropics?
Okay, well, let's look at this figure again. For example, this real fast mode, which is about 1.2 day period, has a big amplitude. Oh, these amplitudes are normalized, so they're arbitrary, but it has a big amplitude at the equator. And this mode has a big amplitude in the U wind at the equator. And in fact, I should say, Hendon and Wheeler have published a paper looking at winds in the tropics and identified variation in the winds with some of these normal modes. So they do affect the tropics. And they're presumably affected by the tropics.
Okay, thank you very much. Next question is by Joshua Munoz. He asks, the appearance of these normal Rossby-Haurwitz modes is in the first numerical models influence the design of the line island experiment?
Would you say again the question, Alejandro?
So he's asking if these modes, these Rossby-Haurwitz modes, influence the line island experiment.
What experiment?
The line island experiment. Lie.
I don't know. I don't know how to answer that. I'm not familiar. What? I guess I'm not understanding what experiment you're talking about.
I guess this is this experiment that NCAR, the first field experiment by NCAR with measurements in some islands in the Pacific.
Oh, okay. I should, since I worked at NCAR, I should be familiar. I'm sorry, I'm not. It's possible. I think these things have to be looked at, really. I don't think, although we've been aware of their presence since the 1950s, which is almost 70 years ago. I really don't think their role in the general circulation or in local circulations has been examined very much. I do know a recent thesis by a fellow from Australia. He looked at the 5-day wave and how it affects local precipitation. So I'm sure there are other variables that might affect some local experiment, but they have to be examined. I don't think anybody knows for sure.
Okay, thank you very much. Next question, it's by Universidad Nacional. And here, it's a pleasure to hear you. I have a question. How do these waves modulate the convection patterns of the tropics?
How do they affect the convection pattern in the tropics?
Yeah.
Okay, again, well, I give example of the recent PhD thesis from a young man in Australia who linked the 5-day wave with precipitation. And I remember, in fact, one of the places that it seemed to show up was on the windward side of the Andes. But again, I got my answer has to be these things have not been looked at.
Okay. Next question is by Manuel Lopez, and he asks, I understand large-scale winds are from west to east, at least the jet stream. Are some of these waves swept by the wind such that they travel from west to east?
Yes, and let me go back to another slide. Oh darn! I forgot to mention my slides were numbered so that if you had a question, let's see what slide did I want to go back to. Oh yeah. Okay. Here, this is what we looked at. This is the results. These are the peaks for the westward propagating, because that's what these normal modes and their periods with realistic winds by Akira Kasahara. So all these in the upper left-hand side, all these waves, one could argue has maximum in this westward propagation. As you go to these smaller scales, you see large coherence, but no peaks in the westward variance. And in fact, this coherence is associated with eastward propagation. So these waves, without winds, should have moved westward, but the winds are just advecting them eastward. And so all the waves whose spatial scales and relative speed is relatively slow end up moving eastward. Again, I don't know if I finished my thought, but the coherence squares are very high. But when you look at the phase, it turns out that the, let's see, I think the sine coefficient spatial leads the cosine coefficient, which is eastward propagation. So indeed, the wind not only advects these things, slows them down, and also advects these things toward the east. It it makes some of these smaller scales not even able to survive or exist.
Okay, thank you very much. I guess that this answers also this other question that asked if these modes, there are some of these modes that actually propagate to the east. So I guess that solved that question.
I think they can't be identified as normal modes when they start propagating to the east, because the wind is comparable to this. The wind toward the east is comparable to the movement that the wave wants to make toward the west, and so that the wave just gets diffused and more or less can't be identified in the data.
Okay, thank you very much. Arturo has another question. He asked, are more field campaigns with radio zones warrant to verify reanalysis products and forecasts?
I'm not sure field experiments, these things are very large scale. And I think we could do a lot more work in comparing weather forecasts and looking at these wave modes in the actual forecast to see if the forecast model handles them well. So I don't think there's any kind of field experiments which tend to be of smaller spatial scale that would help to understand more about these very large scale, like zonal wave number 4 and small and larger.
Okay, thank you very much. The next question is by Chalon Rojas. She says, thank you and congratulations for the presentation. My question is, do you think that these results will change if you use the new ERA 5 reanalysis, and how?
Okay, I'm not real familiar with the difference between these reanalyses, and I guess my answer would be that I don't think the results should change. These, I'm convinced that these large-scale normal mode Rossby waves are there, although one could say there's a little ambiguity with these reanalysis that some of these waves might be built in. But as I showed or mentioned before, the observation of these waves goes back to the 1950s, long before there was reanalysis. And also the waves are evident in various data sets in the stratosphere and in the troposphere that aren't affected by reanalysis. So I think if the reanalysis is a good reanalysis, it's going to show these waves just like the 3 years that I looked at.
Thank you very much. Next question is by Aldo Reyes. He asked, if planetary vorticity is due to Earth's rotation, what produced the relative vorticity in the Rossby's model?
Well, anything that produces any kind of pressure difference that's going to produce winds in the atmosphere, these winds are likely to have some curvature, excuse me, or shear, and that'll be the relative vorticity. So in the model, it's just assumed that there is relative vorticity that's non-zero.
Okay, thank you. Next question is by Adriana Salinas. She asked, can the Rossby waves predict an ENSO phenomenon? An ENSO event?
I would say their effects are not big enough to affect an ENSO event. I mean, for example, again, I go back to this recent paper that showed a relationship of precip with the 5-day wave. It takes quite a bit of analysis to bring that out. It's just not, although what this figure here that I think is very striking, it turns out that I don't think that the winds associated with these waves would be big enough to initiate an ENSO.
Thank you very much. Next question is by Felipe Vargas, but it's also very similar to a question by Daniel Pretelin. So the question is, do you think that these Rossby-Haurwitz waves can affect the seasonal forecast of tropical cyclones? And if can affect the behavior of extratropical cyclones?
Okay, I heard seasonal forecast, and of course the time scales of these waves are longest would be order, 20 days. So they won't affect seasonal forecasts. It's possible that if we do some research, we might find out that some combination of these waves, when they come into correct phase, might be favorable for hurricanes to form. Again, that's something we'd have to look at.
Okay, the next question is by Demian de Jesus. He asks, does the Rossby wave's behavior or movements rely on the atmospheric cells like the polar, Ferrel, and the Hadley cells?
Okay, to the extent that these various cells affect the background wind, then I would say that the Rossby-Haurwitz normal modes are affected, except the very fast ones. Like, for example, this one has a theoretically predicted period of 1.2 days. So that's moving so rapidly that it could be these various circulation cells or mean circulation cells. The winds associated just wouldn't be able to affect these very large scale waves. But somewhere here in this margin where is sort of the dividing line between the existence of the modes and the non-existence of the modes, I'm certainly that large-scale circulation changes could change where that dividing line ends up for a given period.
Thank you very much. I guess there are no more questions, but I do have one very simple question. Is like this normal, the Rossby-Haurwitz modes are solutions to the Laplace tidal equation and in the sphere. And yes. Matsuno's waves are also a solution, but on a beta plane in the equator. But it seems like Matsuno is like Matsuno's waves are like a particular solution to the more general Rossby-Haurwitz waves. Is that right, or is there a relationship between these two kind of solutions, of these Laplace waves?
Okay, let's see. Maybe I go to another figure. Okay, these again, if you remember, are the horizontal structures, are the latitudinal structures of these various wave modes. They're the simple ones in the non-divergent case on a sphere. So I think that Matsuno is looking at a plane near the equator. So let's just take this mode. So I think his solutions would be would relate to those modes, full modes that have maximum values near the equator. I don't think that's really a good answer. I think one other thing I might comment that I meant to say was that the n=0 mode, so this is the one where there's no zero crossings between the poles. These are called Rossby-Haurwitz. These are called, what are they called? Mixed Rossby-Haurwitz waves. No, mixed Rossby gravity waves. And I'm not sure, but I think Matsuno coined that title, mixed Rossby gravity waves. They behave like gravity waves for small equivalent depths, that is, oceans with small depth, and they behave like Rossby waves with oceans with large depth. And for the atmosphere, it's thought that the equivalent depth of the atmosphere is about 10 kilometers, which ends up being a relatively large depth, so that these mixed Rossby gravity waves, this column, behave like Rossby waves. So again, I guess just like the Haurwitz solution on a non-divergent on a sphere, on a non-divergent waves on a sphere is the limiting case for the divergent winds on a sphere of Laplace. I'm sure one could relate Matsuno's results at the equator with these modes. I'm not really able to clearly do that for you though right now.
Thank you very much. I guess it was called by Janai. I guess Janai was the one that called mixed Rossby gravity waves.
They were all publishing in about 1966.
Yeah. Okay. I guess there is a little time for one more question by Arturo. I guess this is the last question. He asked, with respect to barotropic stability, it appears that the meridional gradient of vorticity can only affect high wave number of these Rossby-Haurwitz modes. Is that why we don't see this kind of waves in the analysis?
Well, you would see them in, I just projected the analysis onto these waves. I sort of assumed that the wave was there. And if one were to project analysis onto these waves, you might say that you can see them. The question is, do they have the right period, expected period, and the right vertical structure that you can identify them as normal modes? I think maybe a discussion, we could handle this question better.
Yes. So Rolf, thank you very much. I guess that's all the questions. It's an honor. I repeat again, it's an honor for us to having you here. It's just a shame that you couldn't be here in person, to be here in campus, but I guess that very soon, when all this pandemic ends, I hope to have the opportunity to have you here. Thank you very much.
Gracias, Alessandro.
And I'm going to give the to Carles. So.
Thanks, Professor Roland, for your brilliant lecture. It was really inspiring. Gracias también al doctor Alejandro Jaramillo y a la doctora Graciela Raga por coordinar esta sesión como anfitriones. Y muchas gracias a todas las personas que han seguido esta tercera sesión del Panorama Actual de las Ciencias Atmosféricas 2020. Un agradecimiento especial para las que han participado con preguntas, enriqueciendo este debate. Se les invita a continuar en el evento y seguirlo también el día de mañana a la misma hora. Buenas tardes.